In heat transfer, we end up with problems for extended surfaces, or fins, which are a function of a series of exponentials. So in this video, what I want to talk about is the relationship between the exponential form that you typically see for a fin solution and something called hyperbolic functions, which are simply functions that are used to represent sets of exponentials in a more convenient way. So if we have the solution for a fin problem, which is either given to us in a book or something that we can derive, we might say that the temperature of the fin as a function of position T minus the ambient temperature divided by the base temperature of the fin TB minus T infinity. So this is essentially a non-dimensional temperature as a function of position. When we go through and solve the problem, assuming an adiabatic tip, we end up with this expression, exponential of minus ml times 1 minus x over L plus exponential of ml times 1 minus x over L divided by exponential of minus ml plus exponential of ml. So this is kind of an unwieldy equation. It's a little bit hard to manage all the exponentials. And so it turns out that we can write this function in terms of these hyperbolic functions in a more convenient way. So we say this is all equal to the what's called cosh, C-O-S-H, which is a hyperbolic cosine of the argument ml times 1 minus x over L divided by cosh of ml. This is a bit more compact and concise way to write the same equation. And how do we get to this? And this is kind of the core point of this video, is through these hyperbolic functions and their definitions. So let's go back to what the definition of Cinch and cosh, if you're not familiar with these functions. So let's starting with cosh. Cosh of some argument a is equal to 1/2 times exponential of a plus exponential of minus a. Right, that's our definition of cosh. The definition of Cinch is similar. SinH of a is equal to 1/2 exponential of a minus exponential of minus a. Right, these are simply functions that are defined for our own convenience, but they do have a lot of properties that end up being pretty similar to the sine and cosine functions that we're familiar with. For example, if we take cosh and we were to take the derivative of cosh, d dx of cosh of some function a, that's equal to, remember for cosine to sine, it's a minus sign. In this case, it's a similar transformation, but we actually end up with just plain positive sine, Cinch of a. Okay, the derivative of Cinch, S-I-N-H, of a is equal to cosh of a. So we have this transformation between these two functions where the derivatives actually end up behaving very similarly, not identically, right? Because you have the sign flip in normal trigonometric functions. For these hyperbolic functions, it's a similar transformation, but we can also define this idea of tanh, which is Cinch divided by cosh. Right, so tanh of some argument a equals Cinch of that argument over cosh of that argument. Right, and tanh is also a function that's defined in terms of exponentials, and it would simply be the definition of the two. Right, so we would say exponential of a minus exponential of minus a divided by exponential of a plus exponential of minus a. It helps to understand how these functions actually behave when you plot them out. So let's just kind of sketch what cinch, cosh, and tanh look like. So let's prepare some axes. Let's say this direction is x, and we're plotting, let's say y is a function of x, where y is the evaluation of the function that we care about. Let's also note here where the position of -1 and 1 would be. So let's start with cinch. If we look at the definition of cinch, we're looking at exponential of a number, a positive number, minus exponential of a negative number. So what do we expect to happen as that number increases? The solution is really going to be dominated by that first term, the exponential of the positive number, because it just gets larger and larger, and the second term gets smaller and smaller. So if we plot out cinch, cinch looks something like the following. Right? We see this hyperbolic increase, as an exponential increase as a function of the argument that's being put in. Negative, likewise, it's symmetric, so we're going to see the solution do something like this. Cosh, on the other hand, is exponential of a positive number plus exponential of a negative number. And so it's never going to be able to go negative, right? We're limited in the worst case to exponential of 0, which is 1. So if we plotted out cosh, it would look something like this. So here we have cosh. Tanh is going to behave a little bit differently. So let's pick out tanh, and it's the ratio of these two things. So if you plot it out, it ends up looking something like this, where you have the solution really dominated down to -1. When you get to the x, it will flip, and it'll continue off, converging to +1. Now, there are some interesting properties of cinch and cosh that are worth covering. The first is that if you take cosh squared of some argument a, and then subtract from that cinch squared of that same argument a, that's always equal to 1. Right? Is similar in form to the identity that we're familiar with for sine and cosine, but here we have cosh squared of the argument minus cinch squared of the argument is equal to 1. So this is always true regardless of the argument, as long as it's the same argument in both cases. Others that are worth noting are that cosh of the argument plus cinch of the argument is always equal to exponential of the argument. So this is always true as well. The final thing to point out is cosh minus cinch is always equal to exponential of minus the argument. So these useful properties might come into play as you're doing manipulating some of the equations, but this is more or less the overview of hyperbolic functions and how they're related to heat transfer.